In this video, we're going to look at the effect or the model of dosing a patient with a drug. We're going to consider a patient that's being given morphine at a certain rate, and their body is also metabolizing that drug at the same time at a rate of 30% per hour. So the way these models work is we have to define a variable that defines, in this case here, the level of morphine, or the milligrams of morphine, the mass of morphine in the body. We'll choose the letter M, and with that in mind, what we have are two influences. The rate of change of the morphine in the body, which we can use units to guide us here, that'll be in milligrams per hour, is going to equal the rate that morphine is coming into the body minus the rate that it's going out. So if we can capture both of those elements, both of those ingredients to what dictates the net rate of change, then we're good to go. One of the rates is quite obvious. We're injecting at 2.5 milligrams per hour. So we can literally put that 2.5 in our differential equation. The units for that already match the units that we're looking for. The other element is the loss of morphine, and we're told that it's coming from the fact that the body metabolizes the morphine and breaks it down into something else. This 30% per hour is a multiplier of 0.3 times the current level of morphine. Notice this is sort of a percent per hour or a fraction per hour, so it has units of 1 over hours. And if we multiply that by the current number of milligrams of morphine in the system, it's 30% of the current level, so a product makes sense. We're also going to get units of milligrams per hour. So this is a wonderful model, very frequently used in pharmaceutical industry to model how a drug is processed in the body through the dosage rate and also the metabolism or clearance rate. And it turns out to be a differential equation. What we'd like to do next is predict how that morphine level is going to change over time. How do we get that? We obtain that by solving the differential equation. We have 2.5 minus 0.3 m. Here we pretty much have to take the entire right-hand side and bring it down to the other left-hand side when we're doing our separation of variables. We can also take the dt and bring it up. Where we end up with is 1 over 2.5 minus 0.3 m's dm equals dt by itself. And that's the separation. We also finalize it by integrating both sides. One side's easy, it's just t. The other side's a little more complex, but it's going to be a ln because this is just a linear function of m. We can do this by guessing and checking or by substitution. The catch is, because there's this negative 0.3 in front of the m, if you were to guess this is the integral, it wouldn't be quite right, because if you differentiate with respect to m, you would end up with a negative 0.3 popping out from the chain rule. We want to cancel that in advance, so we divide by that negative 0.3. So with that, and a plus c at the end to capture the two indefinite integrals, we can then solve for m. Why does that leave us? Well, we can bring the negative 0.3 up, and we get negative 0.3t minus 0.3 c's, reminding us again that once we have the c from the integral, it's just a number. We treat it as if it's any other piece of the equation. We then want to get rid of this ln. The way we do that is we exponentiate the entire left-hand side, and of course we have to do the same to the right-hand side. That gives us 2.5 minus 0.3 m's in absolute values equals e to the negative 0.3t, and I'm going to multiply by the other expression because we have a sum or a difference in the exponent. We can treat that as a multiplication down the main line. And then to get into the m at the last stage, we need to get rid of these absolute values. Here we're going to do our semi-standard trick now. We're going to make a new variable called a. It'll package everything to do with a c here as that multiplier. And if it turns out that this absolute value, when we take it away, leaves something negative, we'll make that new term negative. If it's positive, we'll leave it the way it is. At the end of the day, what we're going to get is the absolute value bars disappear, and this whole term here just turns into an a. And what we can see is there's some sort of exponential decay process happening, and if we zoom in a little further, solving for m, negative 0.3 m is going to be let's put the 2.5 first, that'll sort itself out in a moment, e to the negative 0.3t, and when we divide through by negative 0.3, we would get all of this over negative 0.3, which will turn into a double negative is positive, 8.33 minus a over 0.3 e to the negative 0.3 t's. A lot of negative 0.3s running around. But that would be our general solution to this problem. This would describe or predict the amount of morphine in the system over time, given some starting value that would define our A. As a follow-up about our prediction, in the long run, how much morphine will they have in their body? Well, we have 8.33, that's an approximation rounded, but it's the idea. What we can do here is ask what the impact of the long run is. Well, that's a mathematical statement of the limit as t approaches infinity. As t goes to infinity, negative 0.3t in an exponent is going to go towards, that'll be an exponential decay. It's going to approach 0, and so m is going to approach 8.33 minus 0, or the long run morphine level, is going to equal 8.33 milligrams distributed around the body. Perfect. So again, we have an ability to predict into the future based on our understanding of how the morphine is being dosed and metabolized and how those competing interests play out. We can take it one step further and sketch solutions for different scenarios. So imagining our morphine level on this axis and time here, what we found is that 8.33 milligrams is where we're going to end up in the long run. We could also show that that is an equilibrium we wanted. And if we had any level below that, what would happen? Well, we have m equals that 8.33 minus some value e to the negative 0.3t. This is going to be the difference from 8.33. So that difference is going to shrink exponentially over time. We have some initial difference, and then that's going to be scaled smaller and smaller as t gets larger and larger, and that's going to give us graphs that look like this. Exponential decays towards that equilibrium level. If we start higher and we were actually cutting their dosage, then we would still return down then towards that consistent equilibrium level of 8.33 milligrams. We can see that as the last remaining term left standing in our solution.